I want to come back and look a little bit more carefully at a delta-epsilon problem. I don't think this translated real well over the computer in class today, and so I think seeing a little bit more could be helpful. This concept is actually really important, and it's something that's done very carefully in college calculus classes. You actually do something called delta-epsilon proofs. They're not on the AP exam, but I do think the visualization of what's going on here, even if we're not writing the proofs, can be kind of important, okay? So a couple of things here. First of all, this follows the Greek alphabet. This is a lowercase delta. It's kind of like a Greek D. This is an epsilon, okay? An epsilon, kind of like a Greek E, okay? Alphabetically, X comes before Y, so you have your input and your output variable. Likewise, delta comes before epsilon. So delta represents a small change in the X direction, a small horizontal change. Epsilon is a small change in Y. That would be a small vertical change, okay? So imagine I have a function here, and imagine that that's the point 3, 1. In other words, the limit as x approaches 3 of my function is 1. And say they give me an epsilon value of 0.8, and they want me to find the corresponding delta value, okay? What they're saying is, I want to keep my function within a vertical range 0.8 units above and below, okay? The idea of the epsilon delta concept is really that a function has a limit if you can get infinitely close in the y direction and infinitely close in the x direction, and you can keep your function within that x and y range, okay? You remember the problems we did in the investigation where the functions were approaching some kind of a value versus the example that didn't have a limit, in which you had this function that just wildly went up and down very near to the point that we were looking at, and it was never approaching any particular y value because the y would go way high and then the y would go very low, okay? So the idea is epsilon is a vertical change. So if I want to have an epsilon value of 0.8, I'm saying I want to keep my function within 0.8 units above and below the point I'm looking at, okay? Well, if my limit's 1, that's saying I can go as high as about 1.8. So I can go about 0.8 units above, and maybe that would be about right here. So I can go as high as about 1.8, and I can go as low as 0.8 units vertically below, and maybe that would take me down here somewhere, and that would be a value 0.8 units below 1 would be about 0.2, okay? So epsilon is actually this vertical distance right here. That's a length of 0.8. This is the length of 0.8. My diagram's a little small. It's a little hard to draw that in, but you could draw some little brackets there and show that's a distance of 0.8, that's a distance of 0.8. I'm freehanding it, so it's not perfect. The idea here is that you want a range of x values that will keep your function in that range, 0.8 units above and 0.8 units below, okay? So I can go about this far over, and my function will stay in that range, okay? There's that point. All of these values here are less than 0.8 units away from the limit of 1 vertically, okay? All of these points down here to about this point right here are going to be within 0.8 units below my limit of 1. So these are all the values going from 1 down to about 0.2, okay? Delta is a change in the x direction. So we're basically looking at about how wide is it in this direction and about how wide is it in that direction. And based on the scale I'm working with, that width looks like it's probably about 1. That width on that side looks like it's probably about 1 as well, okay? By the way, delta is usually going to be pretty small, and epsilon is usually going to be pretty small as well. I tried to keep the numbers here big, so this would work out. So basically, if I want to stay within about 0.8 units of my limit vertically, I can go about 1 unit out left to right and keep my function within that range, okay? And the concept here is that this is infinitely extendable. So if I wanted to make my epsilon value 0.1, I could zone in even closer, and I could go about 0.1 unit above that point and about 0.1 unit below, and there'd be a very tight range of x values that would keep my function within that range, okay? That would look probably more like this. You know, I could go about 0.1 above, and I could go about 0.1 below, and we have this really, really tight range here of values. You go over a little bit in the x direction, either direction, and maybe my horizontal change there might be like 0.2 or something in those particular cases. I could make my epsilon value 0.01, and there would still be, even if I got super, super close to that point above and below, there'd still be a range of x values that would keep my function within that range. And so the concept here is really that you can get infinitely close from the left and the right and the top and the bottom, and your function will always stay within that range. That's really what it means for a function to have a limit, okay? Meanwhile, if you can't get infinitely close coming from both sides and from the top and the bottom, then your function does not have a limit. And that might be a case where you have a jump discontinuity, some kind of asymptote, or for example, the problem we had where the function was wildly fluctuating up and down. So let's take a look at an actual application here. So a question might say something like, find the largest possible value of delta such that function f stays within, I'm doing an epsilon value of 0.6 units this time, of the limit L as f approaches 2. Okay? They may not tell you the limit. We're going to use the function f of x equals x squared, and you can see a graph here. So the first thing I'm going to do is I'm going to find the limit. The limit as x approaches 2 of this function. If you put 2 in here and square it, you get 4. Okay? So we would be approaching the point 2,4. You can see that point right there. As I approach from this side, I'm approaching 4. As I approach from that side, I'm approaching 4. Okay? So if I wanted to estimate this visually, we want to stay within 0.6 units of the limit, okay? And that just means I can go 0.6 above, which would be about as high as 4.6. But I can also go 0.6 below, and that would take me as low as about 3.4, okay? So visually on the graph, and again, we're looking at this point right here where x is equal to 2. I can go as high as about 0.6 above, which would be something kind of like that. And all these values here would be 0.6 or less above that point. And I can also go as low as about 0.6 below. Okay, and maybe that would look something like that. Okay, delta, so epsilon is our vertical change here. Delta is our change side to side. And you can see this graph's pretty steep. There's a very small width there. That horizontal width is the range that we would have to keep it in. That's probably about 0.1 or about 0.2, okay? Going back this direction, same kind of thing. To keep your function in that range, it's also going to be very tight. Maybe that's about 0.1, okay? The directions will say to find the largest possible value, but you actually want to take the smaller of your two delta values, okay? And the reason is you want a range of values, so if I go to the left or if I go to the right, my function will stay in that range. And if I go back 0.1 to the left and I go back 0.1 to the right, my function will be between the bounds that I was given. If I go 0.2 to the right and I go back 0.2 to the left, it's going to drop down here somewhere and it's going to be somewhere out of range. So you'll always want the smaller delta value of the two. In this one, we're looking at a delta value of about 0.1. Okay? Now, you can also solve this algebraically. Okay? And we'll see how good my picture is. I'm guessing it's not very good. To stay within 0.6 units of my limit, that means I want to be between 4.6. I want y to be between 4.6 and 3.4. Okay? My y value for this function is x squared. So I would like x squared to be between those two values. Okay? Now, if I want to solve for x, I could take the square root of all of this. This means I really want my x value to be between the square root of 4.6, which is going to be about 2.1448. And I can take the square root of 3.4 here, and that's about 1.844. Okay? So basically this says if I keep my function between about 1.844 and about 2.1448, my y value, my function value, will stay between 3.4 and 4.6. In other words, it'll stay within 0.6 units of the limit of 4. Okay? These are not the delta value. The delta is the change in the x. So just like epsilon isn't 3.4 and 4.6, epsilon is 0.6. I'm going up 0.6 from 4, I'm going back, I'm going down at 0.6 from 4. Same thing here. Our x value here that this is approaching, it's approaching an x value of 2. So we want to know how far above 2 it's going. Well, from 2 to 2.1448 would give us a change in x of about 0.1448. Okay? Going backwards here, from 2 back to 1.844 is going to be approximately a delta value of approximately 0.156, okay? Remember, you want the more restrictive of the two, okay? Because you want one that if you go to the left or if you go to the right, it'll guarantee your function stays in that range. And I believe if you go 0.156 to the right, you would end up with values that are bigger than 4.6. So you want the smaller out of the two. And by the way, this means my estimation wasn't too bad. Our delta value is about 0.14, and you can see there I estimated that it was somewhere between about 0.1 and 0.2. I was guessing about 0.1. So anyway, a little bit challenging. Not something they're going to ask on the AP exam necessarily, but still a concept I want you to understand. And the big idea here would be, if I want to make that 0.1, I should algebraically be able to find values of x that'll keep my function within 0.1 units of 4, so between 4.1 and 3.9. And you could find that. And it'd be very, very small change in the x direction. I could make epsilon 0.001, and I'd want something that keeps me between 3.999 and 4.001. And there would be an x range that would do that. And I would have a very small delta that would ensure that. But the idea is I can get as close as I want in the y direction, and there will always be a range of x values that will enable me to keep my function as close as I want to that limit. That's the big idea. So hope that clarifies things a little bit. Still not a simple concept, but I think it should help some.